let's talk about different wave interactions. The term we use in physics for wave interactions is superposition. Superposition is simply the combining of waves at each point. Waves add at each and every point. So if I have one wave that goes, up like this, and let me switch colors. Say I have another wave. We're going to pretend like these are got the same frequency. Ooh, that was kind of funky shape, didn't it? Okay. If this is my equinodal line, I'm going to add these and make them this kind of red color. The zeros, 0 plus 0 is 0, so those are easy. Now, if this is 1 unit and this is 2 units, you literally add them. Alright, so you get these very interesting waveforms. This is superposition, when waves add at every point. And I'm going to show you a diagram. This is wave 1, and 2 is in this hot pink. You see, when we add, we don't always get nice, smooth, sinusoidal waves. We can have what is called constructive interference. Constructive interference is when the waves come together and they're on the same side of the equinodal line, and they add to make a very tall wave. Now, they only add when they're actually in the same place at the same time. And then the waves continue on their own merry way after they pass through each other. So wave A is going to the right. When it's in the same place at the same time as wave B, it adds to be this very tall wave. But then wave A continues on undisturbed. Similarly, wave B, heading to the left, adds when it's with A, but as soon as it passes through, it continues on undisturbed. There's destructive interference. Let's say that wave A is on top of the equinodal line and wave B is beneath the equinodal line. If wave A is going to the right while wave B is going to the left, when wave A and B are in the same place at the same time, they quite literally cancel each other out. So this plus 1 minus 1 adds to 0. But as soon as they pass through each other, wave A continues on to the right while wave B continues on to the left. Now, there's something called partial destructive interference, which occurs when you have one wave with a larger amplitude than another wave. You can see I have this kind of interesting shaped wave, and it is going to the right, while this pointed wave is going to the left. Now, they're not going to cancel each other out completely, of course, because they're not the same shape and the same amplitude. You can see here, as they're coming into the same place at the same time, this, let's call this wave 1 and this wave 2. Wave 1 seems to be losing some of its height until it's down to 0, but that's also true of wave 2. They're partially canceling each other out. But look, as soon as wave 1 gets past wave 2, it gets its same shape, and wave 2 continues on with its same shape. Now, what happens when a wave hits a barrier? There are two things that can happen when a wave hits a barrier. The first thing is it can reflect, okay, and we call this reflection. Reflection is when the wave comes in and bounces off. It can also bend. If it bends, we call that refraction. Now we have a whole unit that we're going to spend on refraction, and it's a really fascinating unit. Let's focus on reflection for the moment. Reflection is what happens when a wave reaches a boundary and it bounces off. Now there are two different things that can occur when a wave hits a boundary and it bounces off. It depends, of course, upon what type of boundary we have. Tell you what, let's see if we can figure it out with this Colorado FET. Okay, here I have no boundary, so I have this wave and it's just going on. I have two choices for boundary. I could have a fixed end or I could have a loose end. I'm going to go to pulse here and let me start over. Let me go to manual. Alright, here we're going to go down to manual, so we're going to move this. Now watch what happens when I have a fixed end. When I have a fixed end, I'm going to give a single pulse. Now, the wave is going to the right. It's going to hit this fixed end, and watch what happens. It bounces. And it bounces and reverses direction. So, when a wave hits a fixed end, it reflects on the opposite side of the equinodal line. Now, what happens when we have a loose end? On a loose end, the wave is able to go up and come back down. And we see that in this case, the wave reflects as well, but it reflects on the same side as the incident wave. Now, everyone loves to do this, and I strongly recommend you get on the FETs and play with them, but you can do all sorts of cool and fun things. Okay, back to notes. On a free boundary, you are going to have a ring, like we saw, and that ring is going to enable the wave to go up or go down, and it reflects back on the same side. While on a fixed boundary, it reaches the end and it can't move and it's reflected back on the opposite side. Now, this is a diagram that if you don't have it, you might want to copy it, of a pulse reflecting from a free end, you can see the ring here, or a fixed end. Now let's talk about tuning forks. Remember, all waves start with a vibrating object. If you take a tuning fork and hit it, you have created a vibrating object. The tuning fork tines bounce back and forth. The prongs set the molecules near it in motion, and tuning forks are designed so that they set these molecules in motion to a frequency so we can hear them. Now let's talk about compressions and rarefactions. On a compression, the air molecules are pushed closer together, so you get a high molecular density or a large pressure. On a rarefaction, they're spread further apart. The density is lower, the air density is lower. And whenever you have a series of compressions tend to have a lot of dots, and rarefactions, fewer dots. Compressions, a lot of dots. Rarefactions, fewer dots. Ooh, that's too many. You wind up with sound waves. Now, sound waves are longitudinal because the sound wave particles vibrate parallel to the direction of the wave. Now, you see here I have a picture of sound waves. Here are the compressions. The light color are the rarefactions. There are fewer molecules in there, so it appears light. You can see the wave is going this way, and the molecules are vibrating to the right as well. Now, we can translate this into a sinusoidal wave. To do that, take the crests and translate those as crests. Take those, the compressions, and translate those into crests. So for every dark space there, that's my crest. And then take the troughs and translate those or the rarefactions, and translate those into troughs. And then all you have to do is complete your sine wave. My sine wave looks very spiky here. So it's hard to draw so small. All right. Now, we also call sound waves pressure waves because they go from high molecular density, and high molecular density means high pressure, to low molecular density or low pressure. And that's repeated by another high density, lots of molecules in there, to low density, high density, lots of molecules, to low density. Now there's some interesting characteristics of sound waves. Remember, the frequency is the number of cycles per unit time. Audible sound is, humans can only hear sounds from 20 to 20,000 hertz. This seems like quite a bit, but there's a whole lot more out there that we can't detect with our ears. If the frequency is less than 20 hertz, this is infrasonic. This is how elephants communicate. Now let's think about this. Infrasonic. So the velocity of sound is about 330 meters per second. We're going to get to exactly what it is in a minute. So when we're dealing with infrasonic, very, very low frequency sounds, we see that we have very high wavelengths. So, very long wavelengths. There is evidence to support that elephants can actually feel earthquakes, which are long wavelength waves of rock beneath our feet. They can detect these infrasonic waves before humans can. Similarly, if it's above 20,000 hertz, this is ultrasonic. Now this is what dogs can hear. Dog whistles don't hurt us. We can't detect those sounds at all, but dogs can. Now, infrasonic waves have very long wavelengths because V is F lambda. So, high frequency is very low wavelength. Low frequency is high wavelength. Now, ultrasound, we know, has a lot of medical applications. That's because these short wavelengths come in and bounce off small objects. So we can see, or detect small objects. But the wavelengths have to be the same size or even smaller, preferably smaller than the object they're bouncing off of. This is what we use to look at babies before they're born. Dolphins use echolocation, and so do bats, in locating their prey, or in the case of bats, and even locating water. One interesting fact about dolphins is their echolocation is so precise, they can determine the size and type of fish swimming in the schools. Now, frequency determines pitch. Pitch is a perception. It's how you perceive the sound, how high or low. So if I were to give a high pitched, then I would perceive it to be a high sound. As the frequency increases, pitch rises. Frequencies are objective, while pitch is subjective. It is a perception. Now, the speed of sound, you remember, depends upon the water. Sound can travel through solids, liquids, and gases, but its speed is actually determined by how close the molecules are. So, closely spaced molecules will transmit the sound much faster than molecules that are very far apart. Now we know there is no sound in a vacuum. In a vacuum, like out in outer space, because the molecules, well, they're not there to transmit the sound. But in solids, a sound will travel very, very fast compared to liquids. And liquids, sound travels faster than gases. Now in air, we say that sound travels at 331 meters per second. If I were to change the medium to a helium gas, we would see that sound travels at 972 meters per second. Now, V is F lambda. So if you inhale helium, and therefore sound will travel much faster in helium, what will happen to the pitch? What will happen to our perception? You get the Mickey Mouse. That's right. That's why your voice, when you inhale helium, sounds so very high. Don't do that. It's not good for you. No oxygen. Now, if you look at methyl alcohol, I really don't ever recommend listening to any sound under methyl alcohol. It travels even faster at 1,140 meters per second. Through solids, like aluminum, it travels at 5,100 meters per second. So sound travels much, much faster through aluminum than through air. Now you remember, it depends upon the medium, and one quality of a medium is the temperature. Now as the temperature rises, okay, the molecules hit more frequently. So sound actually travels faster at higher temperatures. This is interesting. And liquids and solids, you know, the particles are really pretty close together, and so it doesn't affect it that much. But we actually have a formula for the speed of sound in air. And that is, the speed of sound in air is 331 plus 0.6 T, where T is measured in Celsius. I know, we're always measuring in Kelvin, but for this, we're going to measure it in Celsius. So, at 20 degrees Celsius in one atmosphere, so at T equal 20 Celsius, the velocity in air is 331 plus 0.6 times 20. So this is 331 plus, what is this, 1.2? 300, did I do that right? Oh, let's try 12. Can't multiply today. 331 plus 12 is 343 meters per second. What if we wanted to find the speed of sound through air when the temperature is 14.6? All right, T is 14.6. V is 331 plus 0.6 times your temperature. So this is 331 plus 0.6 times 14.6 gives us a speed of 339.76 meters per second.